Hello, everybody. Hello, the YouTube. And today we're going to be talking about none other than the water molecule, the man, the myth, the legend. And this is a picture of him right here, as you see. This is my Mona Lisa right here. Exclusive, exclusive. So we're going to be talking about the water molecule. And undoubtedly, this guy has for how cute he has a lot of weight to hold. And we're going to talk about that. We're going to go in depth in future videos regarding the function of water in our baked creations, how it kind of unites the ingredients together and makes them do their job. Because this guy, this is a factory and he's the foreman. You got to listen to him. For now, we're going to stick to the atomic level. We're going to scope in, look at things up close. We're going to see the water molecule, how it's comprised, and what binds the parts together to create the whole. And I find it to be a very interesting topic, and we'll branch out from there. So that'll kind of be the idea of this channel, is I would like each video to kind of have a narrow focus so to not inundate with information and just kind of break mine one little pebble at a time, so to speak. So we're going to focus on the formula, the chemical formula for the water molecule, and we'll work our way out. Now, you may have heard time and time again people refer to water as H2O. They say, hey, give me some of that H2O. Now, it sounds really cool, but it's not by accident because the chemical formula for water is, in fact, H2O. Now, I like to look at the chemical formula as sort of a code, right? It's a code we have to crack to uh, create the substance in which we are trying to create, this being water. At this point, you may refer to your periodic table of elements. However, I do not have one on me. What I do have is two little cutouts, little makeshift cutouts of what you may see on a periodic table when you're trying to scope for these two guys here. So we have an H and we have an O. Now let's talk about what this means. So the letter in the box here is what is called the chemical symbol. So H would be the chemical symbol for hydrogen, and the O will be the chemical symbol for oxygen. Okay, great. The next thing I want to draw your attention to is the number above the chemical symbol. So the number above the chemical symbol denotes the number of protons or positive charges within the specific atom. So for example, within a hydrogen atom is contained one proton or one positive charge. And protons are located in the nucleus in the center of the atom. Now for oxygen, oxygen contains 8 protons, 8 positive charges. So this is important because the number of protons, and this is something that you have to recognize. The number of protons in an atom, in a given atom, does not change at all, because the second you change the number of protons, you're dealing with a completely different element entirely, and we do not want that. So we're dealing specifically with a hydrogen, which always contains one proton, and we're dealing with specifically an oxygen atom, which always contains 8 protons. Great, so now let's crack the code. Let's build our kind of water structure. So first we need an H, right? We need an H, denoting hydrogen. So I have one hydrogen atom here. Now you may be asking, hey, what's the guy here, little 2? So the 2 is what's called a subscript. Now the subscript basically tells you how many atoms of a specific element is needed. So as a matter of fact, we need 2 H's, not just one. And look at that. I have a second hydrogen atom right here, ready to go. Thirdly, we need an O, oxygen. And that would be this big guy, boom, right there. So that's cool. So we built our structure. We got the atoms that are applicable to creating our water. However, it is important to note we are not quite finished yet, because on their own they still remain whichever elements they are. Separately, they're still hydrogen. These guys are still hydrogen, and this guy's still just oxygen. It's what brings them together, or what bonds them together to form water. So think of it kind of like a family, perhaps, that isn't so close. Maybe it's somebody meeting their second and third cousins for the first time, and they're family technically, but they still feel a bit like this. They're like separate. We need to find a way to bring them together, get them comfortable with each other, bring them together, and eventually connect to form the whole. So that's what we're going to do next. And let me bring another display here to further the point. All right, so here I have listed two types of bonds and the key differences between them. So the key factor I would like to point out here is the electrons, because it's the interaction between electrons of different atoms that essentially forms the bond of which we will be dealing with. Now, electrons, to be more specific, you can look at as the opposite of protons. So we talked about how protons are positively charged and they're located within the center, the nucleus of the atom. Electrons are the opposite. Electrons are negatively charged, and they actually, if you take a look at my little diagram here, electrons orbit around the nucleus. So it's almost like a solar system, if we want to pretend like the H is the sun, and the electron is a little planet that goes around, orbits around. So it's kind of cool like that. It's like the atoms are, a much, much tinier scale of our solar system. One other key point to point out, uh, we can infer, we talked about how our hydrogen here, our hydrogen buddy, has one proton. Hydrogen atoms always contain one proton. We can infer from that, without any outside interference of another atom, that our hydrogen also contains one electron. So basically one negative charge for every positive charge, if there's no outside interference. We will see how that the number of electrons, contrary to protons, the number of electrons can differentiate even between like atoms. So ionic bonds, within an ionic bond, electrons are transferred. Meaning, if we have two kinds of atoms here, one takes from another, and that's how they form their bond. One atom comes along and ransacks the other one for all the electrons that it's worth. But yeah, it's not a very nice relationship seemingly. But however, we can look here. I have listed M and M. M meaning metal and M meaning non-metal. That is, between a metal and a non-metal element, ionic bonds are formed, which actually is not quite what we're dealing with here, because if we're dealing with oxygen and hydrogen both being non-metals, we want to come down here to covalent bond. Covalent bond being between two non-metal elements. Now, within a covalent bond, the relationship is a little bit nicer because the electrons are shared. They are shared. So they come together, they give each other a little bit of help, and that's how they form their bond. So it's a little bit nicer. We're going to go into how that works. All right, so we're going to hammer this point on home. How is this bond formed? Okay, so let's let's come over to my oxygen atom here, my work of art, and I'm going to focus on this guy for now simply because there's a lot more going on. So we talked about earlier how in the middle here is the nucleus. The letter indicates the nucleus of the atom. And on the outside here, you see these rings circling around, and the little dots are supposed to indicate electrons. Okay? The electrons are orbiting around the nucleus. Now, those rings have a name, something we refer to as shells. Okay? Electron shells. Each shell contains a certain amount of electrons. Now, note that there is a method to the madness as far as figuring the maximum amount of electrons each shell can hold, but for the sake of brevity, we are simply going to stick to matter-of-fact statements and say that the first shell, the one closest to the nucleus, can contain a maximum of 2 electrons. Okay? 2 electrons, and you see I have that indicated here, one on top, one on bottom in the first shell, 2 out of 2, perfect. Okay, now we move out to the outermost shell here, the 2 shell, and actually the maximum that can be held here is 8 electrons. Okay, however, we only have 8 to play with, and we already used 2, right? We have 8 to play with because we spoke earlier, and for every positive charge, there is a negative charge, right? So we have 8 total electrons, but we already used 2, so we only have 6 left over to place in the second shell. And I actually have written here to indicate our situation 6 out of 8. So the outermost shell can hold 8 electrons, but we only have 6 to give. All right. Now let's come over here to our hydrogen, guys. And it's a somewhat different situation, right? So we have just the one ring and just the one lone electron, right? One proton, one electron. And that's its outermost ring, outermost shell. And so we're at 1 out of 2 for that. Okay? This is the situation we're in. Now, I want to give some vocabulary because there is a proper term for the outermost shell of an atom, and that is the valence shell. Now, the valence shell is the outermost shell containing electrons, and the valence electrons are simply the electrons contained within the valence shell. Okay? Cool. Now, this is where everything kind of comes together because these 3 guys are all, shall we say, unstable. Yeah, they're all kicking and clawing and scratching. They're unhappy because every atom's sort of goal, so to speak, is to have a complete valence shell. They want a full valence shell full of electrons, the maximum allowable electrons, depending on what shell it is, because it goes further out depending on the atom. It can go further out than just 2 shells. It can go 3, 4. In this case, we're only dealing with 2 maximum shells. So every atom's goal is they want a full valence shell. Now, they can't achieve that on their own, so they need to bond with other atoms. And it's kind of cool how the math ends up sort of checking out because I have my little Mickey Mouse diagram here. This is kind of what happens. So we have our oxygen, and we have our 2 hydrogen atoms, and if they come together and they share electrons, which in a covalent bond, that's what happens, right? Covalent bonds, electrons are shared. They come together, and suddenly, look at that. So we can count real quick. We see the hydrogen here kind of comes together like a Venn diagram with the oxygen. The oxygen gives one of its, shares one of its electrons, and the hydrogen shares one of its electrons, indicated by the little blue guy here. And so look at that. Suddenly the hydrogen has 2 electrons, right? Making it 2 out of 2 here. And same with this guy. We see the same situation, making it 2 out of 2. Now the oxygen, same thing. We're sharing electrons here. So we have 2, 4, and then 6, 8. 8 out of 8. Okay? Because each hydrogen is sharing its lone electron. Each one is kind of coming together and saying, hey, we have 1 electron to kind of share with you each. Let's just all come together. And it's kind of cool how the math checks out like that. Now we got 2 out of 2, 8 out of 8, 2 out of 2. And that's your covalent bond right there. Now we kind of bring everything together, if you recall, our little artwork from earlier where we had the individual pieces but not the whole. I had kind of made these little strips here kind of showing the bonds between each of the atoms, and that's our covalent bond, and that's our water molecule, right? We had the individual pieces, now they're bonded, and now it is Vada. Awesome, right? Pretty cool stuff. So I had a lot of fun making this. I had a lot of fun kind of learning about this stuff and conveying it as well. And so I think next time we'll go into polarity, perhaps polarity, non-polarity, that kind of thing, because that is kind of an important part to grasp as far as intermolecular bonds and connections. So we'll go into that, and yes, thanks, and I'll come back soon with another video. Thank you for watching.